Welcome to the second part of lecture on section 6.2. Last time, we defined E to be the unique number such that the limit as h approaches 0 of e to the h minus 1 over h is equal to 1. If b is a number which is not equal to e, then if you compute the limit as h approaches 0 of this number b to the h minus 1 over h, then it is not going to be 1 because this is only true when this number is e by definition. For example, let's take b to be 2. So I have 2 to the h minus 1 over h, and I take the limit as h approaches 0. So this is not going to be 1, but this is something that we will compute later. Now let's look at this function f, which is equal to e to the x. Then by a theorem we learned last time, we have that f prime of 0 times this number to the x is equal to the derivative of f. And then I'm going to replace this value with the definition using limit. So I have the limit as h goes to 0 of e to the 0 plus h minus e to the 0 over h times e to the x. But by definition 7, this value here has to be 1. And so e to the x is equal to its own derivative. So d dx of e to the x is itself. Last time I mentioned that there are many definitions for this number. One of the definitions that some books start with is to define e to be the unique number such that that number to the x is equal to its own derivative. Now let's compute the integral for the same function. We would get, again, e to the 7x, but then we would divide by the derivative of 7x. So I have 1 over 7. And then don't forget the constant. Now let's compute this integral. I see that I have this e to the x cubed. I want to turn this into e to the u. So maybe I can take u to be x cubed. And du is 3x squared dx. So this is very good because then I can write x squared dx as 1/3 du, and I can perform my u substitution. So I have now the integral of e to the u times 1/3 du, and I get just e to the u plus c. And I just need to substitute back x cubed in place of u. In general, we only consider exponential functions whose base is positive. And there are two different types of graphs which depend on whether the base is bigger than 1 or smaller than 1. If b is bigger than 1, we have this general shape of the graph. These are graphs for 5 to the x, e to the x, and 2 to the x. And you see how the bigger the base, the faster your function grows. So the slope of the tangent line of this graph is just the same value as the function itself, so e to the a. And if the base is not e, if it's something else like 2, we will learn later how to compute this. If our b is smaller than 1 and positive, then the graph is basically the reflection of the 1 over b. So the graph y equals 1 over b to the x is the reflection of the graph y equals b to the x about the y-axis. And all of them have this shape in general. And the slope of the tangent line for y equals e to the negative x. So we know it should be so if this is your function, then the derivative is the derivative of the function at 0 times itself. And at 0, the derivative is -1. So here I have negative e to the negative a. Or you can also come to this conclusion using chain rule.